I think for lack of better term, I'm going to call this Parent Functions and Transformations Part 1. First of all, what is a parent function? The parent function is the most basic form of a type of graph. So let's look at the parent function of the absolute value graph. The absolute value of x. Notice that we have the vertex at the origin, and we can put in the point 1 and get y is 1, and 2, 2, and 3, 3, and 4, 4. And if we put in negative values for x, we would have negative 1, 1, negative 2, 2, negative 3, 3, and so forth. And we get this V-shaped graph that has a slope of 1 on the right-hand side. Every other absolute value graph also has this characteristic V-shape. It just might start at a different point, have a different vertex, or it might be have a steeper or shallower slope, or might be upside down, depending on what we do to the basic graph, the transformations we apply. So let's apply some transformations. We have f of x equals 2 times the absolute value of x minus 3 plus 2. We learned from the worksheet that you did that when we subtract a number inside the absolute value, it shifts the graph to the right, and when we add outside the function, it shifts the graph up. So we're going to start with the vertex. So the vertex starts, instead of being at 0, 0, now the vertex is at the point 3, 2. Now, what does this 2 do to the graph? Well, this tells me that instead of having a slope of 1, we have a slope of 2. So instead of going over 1 and up 1, we're going to go over 1 and up 2. And we're going to continue that pattern, over 1 and up 2. So we have a much steeper slope. Using symmetry, going the other direction, then I would be having a slope of 2, only negative 2 on this side. So also the same slope. So if this is going over 1 and up 2, then if we go back 1, we'd also be going up 2. So we'd have the points that are symmetric to the points on the other side. Now let's apply the same transformation to a different parent function. And by the way, just to remind you, this number here tells me the slope of the right-hand side of the V-shaped graph when I do absolute value. So you can treat the right-hand side of this like a linear equation that you're applying this slope to, and you're just counting up 2 over 1, up 2 over 1, up 2 over 1, and then the other side is just symmetric to it. Let's look at a different parent function now. Let's look at the parent function f of x is equal to x squared. So this is our basic parabola. And if we plotted some points, we would notice that it goes through the point 0, 0, 1, 1, 2, 4, 3, 9. So that would be the right-hand side of the parabola. And since the parabola is symmetric with respect to the y-axis here, it has a symmetry to it. In this case, it reflects over the y-axis. Then we'd also have negative 1, 1, negative 2, 4. Oops, I think I did 3. Let me start over here. 1, 1, 2, 4, 3, 9. There we go. That's better. Negative 1, 1, 2, 4, negative 3, 9. So there is my parabola. Now I want you to notice that if we go over 1, we go up 1. And if we go over 2, we're going to go up 4. And if we go over 3, we're going to go up plus 9. So notice these are in squares. Over 1, up 1, over 2, up 4, over 3, up 9. And this is going to be a pattern that we're going to notice in all of the parabolas that we graph. If it has a 1 here. Now if this number changes, the number in front of the squared term changes, then we will stretch or shrink the graph in the vertical direction. Let's apply the same transformation that we applied to the absolute value graph above. So we have f of x is equal to 2 times x minus 3, the quantity squared, plus 2. So what I did was the function in this case is squaring x. So when I put something inside the function, it means I subtract or add before I square. Just like up here, I subtracted the 3 before I took the absolute value. So that's inside the function. Then I added 2 outside the function, and I also multiplied by 2 outside the function. So let's do the same thing we did with the absolute value graph. Starting with the vertex is at 0, 0. Now the vertex is going to be 3 over and 2 up. So the vertex now is going to be at the point 3, 2, just like the vertex of the absolute value graph. Now, how do I find additional points? Well, there's two different ways. One is I can just plug in points. I can say, okay, I'll put in 4 now for x. So this would become 1, 2 times 1 plus 2 is 4. Oops, I just plotted at 3. So I have the point 2, 4. Using symmetry, the point, the point 4, 4, and then using symmetry, I also have the point 2, 4. Because 2 minus 3 would be negative 1, and when you square it, it's still 1. Then I could put in, so I put in the point 3, put in 4, now I could put in 5. If I put in 5 minus 3, that would be 2. 2 squared is 4. 4 times 2 is 8. 8 plus 2 is 10, so I'm up here. So the graph looks something like this. Now another thing I could do, rather than plotting points and plugging values in for x and finding y, is I could look at the slope. Here the slope was 1. I went over 1, up 1, over 2, up 4, over 3, up 9, using that squared pattern. Now this is doubling the y value, so I'm going to go over 1, up 2 instead of 1, over 2, up 8 instead of 4. If I went over 3, I would go up 18 instead of 9. So this just stretches each of these squares by a factor of 2. So 1 becomes 2, 4 becomes 8, 9 becomes 18. Now this is going 1 over from the vertex in either direction. Now the next one I'm going to do is a little odd. I'm going to look at the parent linear function. The parent linear function is just f of x equals x, and it's the line, the diagonal line when x equals y. Getting a little bit of lag on my drawing here, so hopefully this will change a little bit. Okay, so there we go. Now, if I apply those same transformations to the basic linear function, I would have f of x is equal to times the quantity x minus 3 plus 2. I don't have a vertex in this graph, so we'll look at the origin instead. If I take the origin and move it over 3 and up 2, now the graph goes through the point 3, 2 instead of 0, 0. And then I'm going to apply the slope. If I can get this to quit. This is really behaving badly, sorry. So now if I want to plot the slope here, I know that my slope is 2. So I'm going to go over or up 2 over 1, up 2 over 1, so rise over run, and plot my points like this. I'm not sure why I switched to red, no particular reason. And I'm going to go over 1, down 2, over 1, down 2, over 1, down 2, and keep going so that you can see also see the y-intercept. So I guess I'll put this in black now. So the whole line, notice it's steeper. It has a slope of 2 instead of 1, and it's shifted over 3 and up 2. Now if I were, and notice, I want you to notice the y-intercept is at 0, negative 4 here. Here's my x-intercept is at 2, 0. A quick way to find slope is if I know my x and y intercepts here, then I can also notice the pattern here on a linear graph that I'm going over 2, down 4, or sorry, up 4, over 2, so 4 over 2 is 2, my slope. Just wanted to point that out. Let's put this in the more familiar form of y equals mx plus b, and we'll see that negative 4 for the y-intercept just pop out of there. So f of x is 2x minus 6, multiplying out my binomial here, plus 2, or f of x is 2x minus 4. So we have a line with a slope of 2 and a y-intercept of 4. So I just wanted to show you that the same transformations apply to any type of parent function. And one of the things you're going to be doing is examining a lot of different parent functions and applying transformations to other functions such as exponential, logarithmic, power functions, and so forth.